We're going to keep moving through terms in geometry and start looking at curves, polygons, and symmetry. A simple curve is a curve that doesn't cross itself and it has a starting and a stopping point, kind of like a curve in the road. A closed curve is a curve that starts and stops at the same point. A polygon is going to be a closed curve with sides that are line segments. And a convex curve is going to be a curve with no indentations. We're going to see some visuals in just a minute. A concave curve is going to be a curve that is not convex, which means it has an indentation. So if I look at this, here's some examples of a simple curve at the top. I have a simple curve at the bottom. It's not a polygon because it's not closed. In this one, I have a simple curve, and then a circle has the same starting and stopping point. So it is a closed, convex, simple curve. Here are some additional examples that you can look at for how to categorize these. And kind of if it's not convex, then it's concave. So it's kind of an either or situation with those portions. Polygon regions. Polygons have different regions. You have the interior and the exterior. So what's enclosed in the polygon and what is outside of the polygon. You also have a vertex and a side within a polygon. The vertex is the corner and the side is the line segment that attaches the two corners. Here's another example of a polygon region. Would you consider the point X inside or outside of the simple closed curve? It would actually be outside of it. I've also taken a moment to put all of the names of polygons onto one slide so you have them and they're in easy to locate space. In polygons, we have what we call interior angles, which are angles that are formed by the two sides of the polygon. So they're located at a corner, and it's the angle inside of the corner. The exterior angle is the angle formed from the outside of the polygon. And then a diagonal is a line that's inside the polygon that connects two corners. In here, we have a picture of the interior angle. We also have a picture of an exterior angle. So notice how the interior angle is inside the polygon, whereas the exterior is the angle between a side and a line outside of the polygon. Congruent segments and angles, the word congruent just means equal. So if it has congruent parts, there are parts that are equal. Two line segments are congruent if tracing one line segment can be fitted exactly on top of the other. So like if you were tracing one on top of the other, they would have the exact same measurement. Two angles are congruent if they have the exact same measure. So here are some examples of congruent segments and angles. When two segments are congruent, we use this dash system to show congruency. So when you see a line segment with a dash on it, that's telling you that they are congruent segments. All sides of a congruent and if all sides and angles are congruent, then we have regular polygons. So that means every side has to be the same measure and every angle has to be the same measure. And for this reason, they're equilateral and equiangular. So equiangular means I could take it and I could divide the total number of degrees in the polygon by the number of angles and I would be able to find it. A right triangle is a triangle that has one right angle. An acute triangle is where all angles are less than 90 or acute. And an obtuse triangle has one obtuse angle, no more than one. A scalene triangle is a triangle with no congruent sides. An isosceles triangle is a triangle with two congruent sides. And an equilateral triangle is a triangle with three congruent sides. A trapezoid is a quadrilateral with one pair of parallel sides. So notice how the top and the bottom are parallel, but the two sides are not. A kite is going to be a quadrilateral with two adjacent sides congruent. So that's the defining factor here. And the other two are congruent. So it's kind of like a diamond, but the top and the bottom of the diamond have to be pairs of congruent sides. An isosceles trapezoid is a special trapezoid that has two parallel lines, but also the two sides are congruent. And that means the two base angles are also congruent. A parallelogram is a quadrilateral where we have two pairs of parallel sides. A rectangle is a parallelogram that has a right angle in it. So we have two pairs of parallel sides, one of which has a right angle. A rhombus is a more specific parallelogram. There's no requirements for the angles, but all the sides have to be equal, which brings us to a square, which a square is like a rhombus, but every angle is 90 degrees. There's a requirement for the angle in a square. There is not a requirement in a rhombus. So this is kind of our hierarchy. If you're a polygon, you could be a quadrilateral. And if you're a quadrilateral, you fall into this family over here. So if you're in a quadrilateral, a kite could also be a rhombus, which could also be a square, or a trapezoid could also be called a parallelogram. And then you have rectangles, which can be a square if all four sides are equal. So some of these lines are connecting different names for different shapes. Now, if I'm looking at symmetry, symmetry means that I could fold an object in half, and the line that you would fold it in half would be perfectly on top of each other is called the line of symmetry. So if you start looking at each of these objects and you consider how many different lines of symmetry does it have, if I look in part A, there's a lot of ways I could fold that shape and get the exact same shape. So there's 6 lines of symmetry, and if we count our corners, 1, 2, 3, 4, 5, 6, I have 6 corners. Something to consider there. If I look at the letter A, I can only fold it in half vertically. If I start trying to fold it horizontally, it's not going to be on top. If I'm in C, there are 2 different ways I could fold that, and that's going to be the same for circles as well. And if I look at this odd Z, there's no way I can fold it, because if I fold it in half horizontally, I'm going to have one side on one side and one side on the other. If I rotate something, it has rotational symmetry, or what we call turn symmetry. So that means if I'm turning the object around, it's going to look the exact same no matter what the turn was, or if there's a specific degree. So if I take this triangle and I turn it 120 degrees, it's going to look the exact same. So if I look at the turn the rotational symmetry for each of these objects, in part A, I have 72 degrees because I have these little triangles, and when I rotate them 72 degrees, I'm going to be able to get that rotational symmetry. We should probably take note of how many triangles there are there for that. In part B, I'm going to be able to rotate this 60 degrees. Those equilateral triangles have 60-degree angles, so when I rotate them 60 degrees, it will put one triangle on top of another. And in part C, I would have to completely flip it horizontal, like make one complete flip in order to get that rotational symmetry. Point symmetry would mean that it has rotational symmetry at about 180 degrees to have point symmetry. So if I look at each one of these, if I rotate them 180 degrees, I'm going to have the same shape. Geometric figures in a plane can be classified by the number of symmetries they have. We can use those lines of symmetries to define various types of quadrilaterals using geometry instead of just using the sides and the angles. So if I have a triangle and it's going to be described as having exactly one line of symmetry and no turn symmetry, the fact that it has no turn symmetry means it's not equilateral. And the fact that I have exactly one line of symmetry tells me that only I have to have 2 congruent sides on either side of that line of symmetry. So I'm able to deduce that this is an isosceles triangle.